There are lots of different bridges, and each one claims to be the bridge that bridges them all. And this meme sums up the current state of bridging. The situation is that there are 14 competing standards, and then 2 people show up and say, "That's ridiculous. We need to develop a universal standard that covers everyone's case." And now there are 15 competing standards. So every bridge claims to be secure, but bridge hacks total over $1 billion. Every bridge claims to be decentralized, but some are controlled by a multisig. Every bridge claims to be the best, but are extremely specialized, only bridging Ethereum to another chain and only for token transfers. So who will win the bridging wars of crypto? Well, we don't have to guess because there is already a war in which protocol would rule over the internet. Spanning over the 70s to the 90s, there was a huge power vacuum on who would connect the internet. And lots of tech companies wanted to control the internet, being the only ones to sell this solution. So that's where we get the protocol wars. MIT developed ChaosNet in the 70s, the Xerox Corporation developed XNS in the late 70s, the Digital Equipment Corporation developed DECnet in the late 70s, early 80s. IP was developed in collaboration with over 5 organizations in the early 80s. Apple had developed their own solution, AppleTalk, in the 80s. IBM and Microsoft developed NetBIOS in the 80s, and Novell developed PX and SPX for their NetWare network operating system. Now, which one of these do you recognize today? If you're watching this, then you have and have heard of an IP address, meaning you're using the IP or Internet Protocol. But why do we call it the Internet using the Internet Protocol and not the AppleNet using AppleTalk? Why specifically did IP win? First is that it was general rather than specialized, unlike AppleTalk, which required special hardware only for Apple computers. Second is that there is no patents and was open source. Third is that it was contributed with multiple organizations not for making money, but for the goal of connecting computers. So IBC aims to be a decentralized, secure, and trustless bridging protocol for all of Web3. And this video is sponsored by the modular IBC hub, Polymer. Polymer is extending IBC beyond the Cosmos, bringing interoperability to Ethereum, Celestia, and Cosmos ecosystems, allowing for rollups, roll-apps, and app chains to communicate. You see, Polymer have been great contributors to IBC, contributing to open source, hosting events on IBC, and writing educational articles. So Polymer is a very fitting sponsor for this video. Go check them out because without them, this video would not be possible. So in this video, I'm going to talk about OSI Model and TCP/IP, the requirements to enable IBC, the layers of the stack and relayers, IBC's light client proving mechanism, IBC connection, channels, and packets, go through the IBC life cycle and explain why no bridge is like IBC. So let's begin with the OSI model and TCP/IP. On the internet, we have standards for transporting data. These standards are called TCP/IP standards. TCP means Transmission Control Protocol, and IP stands for Internet Protocol. The internet can be divided into 7 layers in the OSI model, the Open Systems Interconnection model, which really breaks down into 4 layers with the TCP/IP model. At the top is our application layer. This is the actual data and how it's presented to you on the internet. Then at the bottom, we have the network interface layer. This is how data gets from your computer either through a Wi-Fi router or Ethernet cable, through physical wires in the earth, then to other computers. But these 2 layers in between, the transport and network layer, aka TCP/IP, is how the data knows where to go, which is essentially bridging information from computer to computer. And that's how modern day networking protocols of the internet work. So with the TCP/IP standard, these isolated computers can connect together, making an easy and seamless experience that we call the internet. And this is what IBC does. It's a standard for formatting packets and relaying them from chain to chain. So let's learn how IBC works. But first, what are the requirements to use it? There are only 2 requirements. 1 is finality and 2 is global consensus. Finality means all transactions must be final and can't be forked or reorged, meaning no native support for chains with probabilistic finality or proof of work like Bitcoin. And second is global consensus. This requires the whole chain to be on the same consensus, so there's no native support for federated consensus protocols like Stellar Lumens. And that's it. Those are the only requirements to integrate IBC. Now that our blockchain meets these requirements, let's start with architecture. So first you have a blockchain with its user, application layer, and IBC module. Typically the Cosmos SDK Go implementation has ABCI++ and Tendermint or Comet BFT. But both of these can be replaced because IBC isn't only for Cosmos chains. The way these chains connect is through a relayer. A relayer relays, which means to receive and pass on, packets of information from blockchain to blockchain. Current implementations of IBC are light client based, but other projects like Polymer are using different proving mechanisms to expand IBC beyond the Cosmos. The reason why IBC's light client verification system is important is because when bridging, How do you prove that something has happened? These blockchains are only verifying themselves. So how do you prove to a chain that you have burned money on blockchain A so they could mint some new one on blockchain B? And this problem is why bridging protocols are really hard to make, and why some just rely on a centralized third party. But IBC bridges in a decentralized fashion with these two cryptographic methods. First is Substore. Substore is a subset of paths within a chain's key value store that are reserved for IBC-related storage, which are specified to enable lightweight proving algorithms on the counterparty. When using IBC, chains need to keep track of foreign state. They have a dedicated space called a substore that holds the counterparty state like this. It's a key value pair that says the transaction path, so where it is, and the value of the state. Let's say transaction C is an IBC transaction from blockchain A to B. Chain A would then keep a path and a state in a substore. And to prove that this substore is correct, the other chain, chain B, only has to keep something called an app hash. It's a compact hash of the whole chain state, including the IBC substore. So on one side, we have chain A's IBC transaction state in a substore, and on the other chain, we have an app hash. But how do we prove validity of these IBC states in a substore? How exactly do we prove state inclusion? And this brings us on to our second cryptographic method, Merkle Proofs. Merkle Proofs is how you prove state is included by verifying the data structure of a blockchain, which are called Merkle trees. So let's say we have 8 transaction states, A, B, C, D, E, F, G, H. These are our Merkle leaves. You can hash these up together, and a hash is sort of like a cryptographic ID. So every 2 of these get combined up all the way to the top. So Merkle roots are a compact representation of all the Merkle leaves, in this case a blockchain state. So to prove inclusion of state, specifically our IBC Substore state, all we have to do is combine all the uncle hashes and include the individual state that we want to prove. So to prove the inclusion of C, we need to prove the uncle hashes, A, B, then include the individual state we want to prove, which is C, then the rest of the uncle hashes, D, and then finally hash E, F, G, H. So we can prove that our IBC transactions are valid by proving that chains B app hash can make a Merkle proof using chains A substore, and you can be confident in bridging once the app hash matches the Merkle proof just made. So our app hash on chain B, A, B, C, D, E, F, G, H, matches the Merkle proof we just made, A, B, C, D, E, F, G, H. The benefit of these two methods is instead of keeping all of these IBC transactions and constantly updating them every single block between both chains, chain B can just keep a small app hash, and chain A can keep the IBC transaction states in a substore. And we can always prove validity if we show the Merkle proof matches the app hash. So with this core concept, we can now bridge. But before we do any bridging, let's first start an IBC connection, create channels, then finally get to IBC packets and their lifecycle. IBC connection. IBC connections are sort of like established IBC ports for IBC channels to connect to, and they network using the handshake protocol. First, we have the interface connection end. This identifies the connection. Then we have the state, which is the current state of this connection. The counterparty connection identifier. This is the ID for the other chain's endpoint. The counterparty prefix. This is the commitment prefix to understand how they verify blocks. Then the client identifier. This shows the IBC client, like which version of the IBC module you're using. And the counterparty client identifier shows what the other chain's IBC client is. And then finally, version, which is a simple string which shows which version of IBC the chain is using. Now that we have a connection, we can add an IBC channel or multiple channels. These can be ordered or unordered for private use or a specific use case, like only for certain functions, but most of the time you're going to be using an unordered general purpose IBC channel. And this IBC channel is going to have 4 states. First is init that starts the channel and opening handshake. Second is try open, which gets an acknowledgement from the other chain. Third is open, which means the channel is open, and closed means the channel is closed. So now that we have an IBC connection that establishes a port, IBC channels which connect to these connections, now we can send these IBC packets. And here's the format in which this information is sent. Our packet interface has 8 objects: sequence, timeout height, timeout timestamp, source port, source channel, destination port, destination channel, and data. First, we have sequence that numbers these packets. Relayers must relay earlier packets first. Second and third is timeout height and timeout timestamp. This is the block height and timestamp in which packets are no longer valid. Fourth and fifth is source port and source channel. This is the IBC connection of your chain and which channel you're using. Then destination port and destination channel is the IBC connection of the other chain and which channel they're using. And then finally, data. These are bytes of data that are interpreted by the other blockchain. So once we have all three key components for an IBC transaction, IBC Connection, IBC Channels, and Packets, we can now go through the IBC Packet Life Cycle. So here's a life cycle of an IBC packet. First, the user interacts with an application and wants to make an IBC transaction. Let's say from chain A to chain B. A relayer will query this packet of data from blockchain A and send it to blockchain B, and prove validity with a state commitment and Merkle proof. Blockchain's B IBC module will pick it up, send it to the application layer. The app layer will verify this cryptography and tell the IBC module that it acknowledges it. The second relayer will query this packet of data from blockchain's B IBC module, send it back to blockchain's A IBC module to then send to their application layer and acknowledge it. And just like that, information was seamlessly, decentrally, and easily transferred between two blockchains. But here are some other things you didn't notice about IBC versus other bridges on the market. First is that IBC is 100% free to implement. IBC is decentralized and open source, so multiple teams all across the world contribute to it, and there are no special hardware requirements, no paywalls, or walled gardens. Second is that anyone can be a relayer. You don't have to be a validator, and you don't even have to be a full node. And instead, relayers can just be light nodes. Third is that even though Tendermint created IBC, the Cosmos hub, and its token Atom, Atom is not required to pay for relayer fees. Instead, relayers get to decide on which currency they get paid in. And remember how I was talking about walled gardens? Well, with other interoperability solutions like Polkadot, fees must be paid in DOT and only be interoperable with Polkadot's blockchains. Fourth is that anyone can relay packets and you don't need any special permissions. IBC was even designed that the relayer who started the packet cycle doesn't have to be the same one that ends it. Fifth is that there are no centralized custodians. IBC is just a message transferring protocol, so relayers at no point in time can ever access your money. Sixth is IBC's incredible safety. If light clients act malicious or in any part of the IBC lifecycle, a packet gets stuck, after a certain amount of time or blocks, your money just gets brought back. The seventh and one I say for last is that IBC is more than just for transferring tokens. IBC, being the inter-blockchain communication protocol, means that it's extremely generic and allows for lots of customizability. Allows for things like interchain accounts, where one account from one chain can manage accounts on other chains. Things like interchain queries, that means you can request and read data from other blockchains. Another cool feature which is rarely talked about are solo machines. Solo machines allow IBC to connect to a single centralized computer. This can be used for real-world asset issuance on-chain like stablecoins. There are also a lot of other cool things you can do with IBC, but the last one on the top of my head is multi-hop, which, by the way, shout out to Polymer because they're the ones that are developing that feature. Multi-hop allows you to relay IBC transactions through multiple blockchains. So my conclusion is the future standard of blockchains is IBC. Because it took inspiration from TCP/IP, IBC is truly the bridging protocol for the Internet of blockchains.